I just want to show what we did last time. We actually put an equivalent circuit of that. All that is difference now between the earlier common source was that there is a source resistance which is not bypassed by the capacitor even for AC. Okay, yesterday's question was asked something where is the biasing, that RG actually was RG1 parallel RG2 to the VDD and is equivalent for a AC RG is appearing. Okay, is that clear? So someone asked where is the bias, so you should know that it must have been coming from the bias network. Okay, those who were, there are many people ask me what is it. The word origin stands from where it comes from. Okay, so some parameter is in the equivalent circuit coming, so from where it comes from. So for example a capacitance, why it is there or how from where it comes. Okay, in the circuit device side how it comes. Okay, so that was the word origin. So I don't know why there was a confusion, but if so please remember thoda English mera different ho sakta hai. Okay, so this is what we did last time. We calculated the gain function last time. The current voltage gain is roughly equal to RD parallel RL by RS, and we said what is the advantage of this? The advantage is that none of the two parameters of none of the two numerator denominator terms have device parameter dependence, no beta, no GM or whatever it is, and therefore it is no even temperatures, and therefore it is very stable amplifier at the cost of reduction of gain. Okay, so this is why we still use these amplifiers. Then we also did something about the common drain or source follower. Essentially the difference between the last one and this is that there is no drain resistance. RD is 0, in this case RD is 0, that is why it is common drain, it is going to the ground, drain is going to the ground, and the output is taken at the source itself, output is taken at the source, and this is that source resistance RS, this is additional load resistance if it is there. This is that RG which is the bias equivalent resistor RG1 parallel RG2. This is your signal, this is R signal or R series whatever you call as the source resistance. That source word is coming common, source in the sense signal source resistance. Okay, and then we say we want to find the gain of this amplifier. Initially we assumed R0 is very large, infinite, we opened it. Then this is your RD, I made it 0, that means drain is grounded. So this RD even if it would have been there it does not matter, but essentially this node itself is grounded. I am picking voltage at the source end. There is a RS and there is the external load RL. Okay, and please remember I am taking simplicity, R0 is much larger. What does technology wise it means? If R0 is very high, two possibilities exist. When R0 will be very high, lambda is very small, close to 0, or IDS is very small, you are operating at very small drain source current, but at that case what is the risk you may have? If the currents are very low, what does that mean? The device may not be in active mode, or it may be just the edge of active mode, it may be closer to off state. Okay, so too low a current is not possible, and too high a current will take the device out of saturation into the linear mode, and therefore again we do not want to work there. Okay, so this is the equivalent circuit. What is the advantage of MOS over bipolar? One of the interesting thing it gives you that there is no connection between gate and source. Okay, DC current, there is no DC current between gate and source because of insulator. In the case of bipolar, what was that? Base emitter junction exists. Okay, and that means IB flows both through the emitter as well as through the base. This fact is not there in MOS. So it is much easier to evaluate, because if there is a current common to two sides, then you have a problem to hold. Okay, so this is what we were doing last time, a source follower. And why word follower? I said output must follow the input. Can you tell me what two things it should do when I say output follows input? for any such voltage or current gain or transfer gains, what are the two parameters are associated with that? One is the magnitude, the other is phase, okay, phase. So when I say output follows input, it should follow in both sense. What does that mean? Amplitude wise it should be roughly same, and phase wise also it should be same, that means zero phase difference between input and output. This is a major difference from common source amplifier which we did. What is the phase difference there? 180 degrees. So the first thing it will be different, that it will be, and therefore it is much easier because gain is unity and phase is 0. So now you can connect some input side to the output side without any great difficulty. All that we must do is input resistance and output resistance should be tolerable, so that we can use them as a in between buffer, either say B or either say B. Yes. Oh yeah, you are right. You are very. I am sorry. I fully apologize because you know that RS, the same old this idea. You are right, very right. Sorry, you are correct. Okay, actually that is how we did, because then we said Vn. Okay, the next equation will come, that then this Vn is equal to how much? This volt plus drop across Rs. Is that what your point of view is taken care? If this is not grounded, then there is an issue will come. VGS will be equal to Vn in fact. Okay, but that is not true. What you are saying is very correct. This input voltage then is, and assuming R series is 0, this voltage plus this voltage is actually the Vn. Is that correct? Do you understand this? No. Rg of course is across it, so it does not have any problem. Across that is VGS. Across VGS is across Rg. So voltage across Rg is VGS plus drop across Rs must be equal to input voltage if this resistance is 0. Okay, is that okay? So this, his point of view is very correct, otherwise that equations will go awry also. Okay, very good, thank you. Okay, having done all that analysis, one can immediately say, one can write RSL is the parallel combination of Rs and RL, R0 is treated infinite. So Gm VGS RSL upon 1 plus Gm RSL, and VGS is Vn, Ig is 0, AV is Gm RSL upon 1 plus Gm RSL. If Gm, actually you need not say even RSL, we should say Gm Rs at least should be larger than 1, then 1 can be neglected, the gain will be close to 1, but it will always be less than 1, is it clear? It will always be less than 1, because 1 plus something, even if that quantity is much larger than 1, still numerator will be smaller than the denominator by small quantity if not greater. So AV will be always closer to 1 but never reach 1, and since the gain is positive here, what does that mean? Phase is 0, okay, same phase. So output and input has gain of 1, means output follows input magnitude wise as well as phase wise. This is therefore called source follower. Is that clear? In between equations I am not doing because we did it. Please remember, circuit solving is identical. Use this voltage equal to this current is only flowing through this. Please remember I0 is only flowing through Rs and RL, okay. That current is equal to Gm VGS, okay. Just write the equations as we did for common source, and same equations, similar equations can be derived. Yes. Yeah, in case, if I wrote somewhere it is wrong, because essentially, okay, I think that term should not occur. Okay, this is not correct, you are right. But anyway, this may not be correct, but this other terms are correct, okay. No, it should be then Vn, VGS, then you must actually replace VGS by Vn in terms of, please remember, then I must replace VGS in terms of Vn, okay, and then substitute Vn. Assumption is I may tell you GMRS is smaller, RS is smaller, drops are smaller, in that this gain will come close to 1. Otherwise this 1 will not be 1, it will be 0.95, 0.93 or 0.98 maximum. The value which I calculated to show close to 1, so I wanted to remove things so that it becomes, but in real life what she said, we must solve the network as it is and get V0 by V in whatever terms you get. Is that correct? This was done to show, my only aim was to show you that it is close to 1. So I made mischiefs so that I can get close to 1. Okay. What will be the, for example, here is something. If you have an RG and R series, the VGS will be something related to that, okay, as we did earlier, and then we must find Rin and RG again as normal devices, okay. Please look at it, this solution I do not want to do it, I just want to show you how do we worry about the solving a network. Is that clear? What is the game? Just draw equivalent circuit, put voltages as given to you and see which loops are you are getting to solve. Solve the 2-3 equations. If 3 unknowns come, 2 unknowns, 2 equations, you should be always able to solve all parameters in terms of the other. Is that correct? That is the technique we will follow throughout the course. Is that okay? That is the course. For example, even in a common source, someone asks you to find not common source, this source resistance follower. There is a RS here, there is a R0 here, and please remember that RS is the source resistance, R0 is the load resistance, output resistance. And why did I show you the opposite sign? Drain is down and source is up. Please look at it, drain is down and source is up. Common drain, please look at the circuit, it is a common drain. ये थोड़ा सा करते आना चाहिए. Drain is grounded. Drain is grounded. So it is the opposite. This from here, this is current is entering the source side. So is from here the RS is going to the ground. So RS and these two are in parallel. Leaving RL. RL is external. So these two are in parallel because this source is now coming from ground towards source. So the signs which are used there, if you see clearly, it is showing upwards. Then this is RS. How do we calculate the output resistance? What is the method I suggest? Short all input side sources, independent sources. Put at the output Vx as the source. Assume Ix is the current starting from here. The ratio of Vx by Ix is the output resistance. We are looking into this side. Okay. So what we do is, we check this equivalent circuit. This side I already grounded, okay, this side we already grounded. So I get Ix, please remember where is VGS, not this, VGS is here, please look at, this is gate, this is the source, is that correct? Output resistance is calculated where? Please keep looking at the source. Is that clear? Looking at the source, this is my output. So the output resistance is looking at the output side. Which is my output side? This is my output side. So I must look out. Is that clear? Source follower, where is the output taken? From the source. So the output impedance should also be seen into the source. Okay. So if I do that, which I did here, the output, this is my source, this is my drain, and this is my R0. Is that okay? So this is source, this is drain, this is current source, this is RS, this is R0. So I write Ix plus Gm VGS is Vx upon Rs current through this, Vx upon R0, but Vx is minus VGS 0. Why? This is grounded, no current between any of them, okay, this is grounded. So no current between source Rg and R series. So this is equal to minus VGS. This is minus terminal, this is plus terminal. Why it should be plus at the gate? Otherwise no current can flow. VGS should be greater to make it current flow in the transistor. So VGS has to be plus here, minus here. Is that okay? So if I put Vx equal to minus VGS, then I resolve these expressions. I get R0 is Vx upon R. So you can see it is Gm Vx plus Vx upon 1 upon Rs plus 1. Gm can be written 1 upon Gm. Gm can be written as 1 upon Gm plus 1 upon Rs plus 1 upon R0. What does this 3 1 upon means? The 3 are in parallel. So 1 upon Gm parallel Rs parallel R0 are the this is the output. Of course here I actually converted back, but otherwise these 3 resistances are in parallel. That is the output resistance of a source follower. Can you now see, is R0 very large compared to Rs? Which one? No, this is R0 will be, this is R0, no? Oh yeah. Oh sorry. Oh you are perfect actually. 1 upon Gm parallel, sorry, no, just right, Rs parallel. Yeah, you are perfect. That has to, it's a parallel combination. No? So 1 upon R is 1 upon R1 plus 1 upon R. Yeah, perfect. Oh, that for the calculation of load output resistance, we should say load is outside, because it's not our making, it is someone else is going to connect. But when I want to have a load voltage calculation, I use that. Why? Because I want to know if that appears, how much is I am going to actually get the output voltage. Is that clear? But the measurement is R0 is for what? This device as an amplifier, how much output resistance it is giving, and with which it should get compared. Then your point of view is well taken. R out is parallel to RL, and now we must see whether this is good enough or not good enough to change the output for the input for the next stage. Is that clear to you? That is exactly what we are looking. How much is this R out compared to the load, which will whether affect it or not affect it. Is that clear? That is what we are really looking for. Okay. So we first find out what is the available R0 for us. Okay. So this roughly finishes the source follower. What else we have to do? We have said common source, then we did common source, sorry, this is Vx, no current between these two, this is grounded, this must be grounded, but the signs are plus minus. Is that okay? So this potential is minus of VGS. This is 0, input is 0, no current between resistances, this potential is therefore equivalent of a ground, this is 0 and this is Vx, but the definition is this is plus VGS. So Vx must be minus VGS. Is that okay? Circuit wise, is that okay? Yeah, sure. I am sorry. You should, the way you did, thank you very much. Keep doing this. Yeah. Always looking at the device side loads, not external load, leave it. Always look at inside the transistor. Okay. Always look inside the transistor. Okay. If someone may ask you actual output resistance as seen by the load, external load, then put RL parallel to that, whatever it is. Okay. RO dash you may call it, and then parallel of actual load, external load with this RO you have calculated. This will be always in parallel. Okay. But in common source the output is taken at the drain end. So we look at the drain end, the output. Wherever your output is, you look into the drain. That point. Okay. Here it is in source, so I looked into source. Is that okay? Always remember, wherever is the output, without external load, whatever impedance seen there is the output resistance. Okay. What is our actual game later we will want to do? We are going to work on something called feedback systems, and what are we trying to do there? We actually want to change gains. I mean, we don't want to change gains, but they will change. But we will be able to control this R in and R out. That is exactly what feedback does. Okay. And we will say why other feedbacks are more important for what we call stability. We have not done multi-stage so far, and we will see what happens if there are more than 2 or 3 stages of an amplifier. We have first stage amplifier, output of that is given to the second stage amplifier, output of that given to third stage amplifier, maybe n stages. How can we go n stages? What are the maximum number of stages you can give? And if there are odd stages and if there are even stages, what will happen to the output input relationship? That is exactly what we will do in multi-stage, okay. And then we will see, oh, then it is becoming like a oscillator and not even oscillating. What is the word I said? What does that mean? Can anyone think? I say it is not an oscillator, but it is oscillating. What does that mean? Oscillator is fixed frequency. Is that clear? Oscillating does not mean that it is a fixed frequency. Say it is varying, amplitude is varying and phase also is varying, okay. That is called oscillating systems. What is oscillator? It oscillates at one frequency. That is the difference. So amplifier, the difficulty in amplifier designs is something like this. When I try to make a good amplifier, it starts oscillating. It is called unstable. Okay. Whenever I start actually designing an oscillator that it should work as good this, it will start giving amplification. Okay. Then we are worried it is amplifying. So design is interesting, that when you want to control this, something goes away. So control that, this goes away. So how do we match? That is all the circuit design is about, okay. Here is another last configuration maybe we will do, which is common gate configuration. Okay. We have done common source, common drain, finally common gate. Okay. Without thinking too much, you just draw this circuit and think why someone should do common gate at all. This current source is given to V minus, this load, sorry, this is RD, is going to be VDD. Oh, this is IQ, is going to minus V, or call it VSS. Okay, it can be also 0, but I just as a generalized I say it goes to minus. Okay. Please remember it cannot go to plus. Why? Current direction नीचे दिखा है ना, तो ऊपर तो नहीं जाना. ये थोड़ा सा एनालिसिस करते ध्यान रखो, यदि करंट सोर्स नीचे दिखा है तो पोलैरिटी ऐसे होनी चाहिए, ऊपर पॉजिटिव पोटेंशियल, नीचे नीचे माइनस आना चाहिए, अदरवाइज नीचे क्यों गया वो. What I say is current source direction is at the end current source is receiving V minus voltage. Okay, it can be even 0. Okay, it can be also 0, but it should not be positive. Okay, and I told you yesterday there was a query, small one of the 5 queries. The major thing in analog circuit which is different from digital, it is all many times or most of the times dual rail. 2 power supplies plus VDD minus VSS or VSS with which is a minus of that. Okay, this is always analog circuit uses the advantage. Has anyone found this? What's going on? Why should have a 2 rail supply in the case of analog? Digital we don't want it because there is nothing called minus voltage detector as 0. Okay, so I don't want that. Okay, but in the analog I will prefer if it is minus volt to plus volt. That means 0 is shifted. क्यों ऐसा कर रहा हूँ? There must be something I am getting advantage by putting 2 rails. Okay. Typically voltage difference may be same. Let's say I have a 5 volt, so I will put VDD 2.5, VSS minus 2.5. So the net difference is still 5 volt. Okay. But I will prefer instead of 5 to 0, which is called single power supply device circuits, single power supply circuits. They are also possible. But on preference to them, I will say, oh, instead use VDD VSS, half or whatever difference you want. You need not be even half. There may be different values can be given. Okay. Is that okay? So we like to see, if not, next Wednesday first thing I will tell you why minus is advantageous, okay, in analog blocks. Okay. Do you see any disadvantage of this having minus in the case of silicon circuits if I make on chip? Do you see any problem if I have this? No, VT ka koi baat. See, there are 2 power supply I have to create, one is plus and one is minus. Either externally I must supply you minus and plus, or internally I will have to create some minus by shifts something. level shifters I will have to put. Thirdly, I may have another problem that I have two lines running everywhere, one plus, one minus. In circuits, in integrated circuit, every micron or every nano now is of importance. If I unnecessarily run power supply lines everywhere, I am losing that much area, I am not doing anything with them. So I would actually prefer one VDD. Okay. But still analog people say, please Baba, if you can, give us two power supply, two dual rails. Okay. That is most important. Not that it is great advantage that I am trying to make. Don't think that बहुत कुछ भगवान होने वाला है, nothing. But there is still positive advantage. If there is something problem of something, I may give one word also, reliability issue. There is something happens if otherwise. So think of it why we still go for minus voltages. Okay. No. RS is the actual part of the capacitance is for the external load. When the signal goes to the external side, I want to know how much is the external load. Then I do not want DC to be connected at the output which is external to me. Okay, there I do not want DC to go. Is that clear? No, here it is not so. Here this CG is different from that. No. This is my device. This is load, actual load of the transistor. This is external load. So before I get external load here, I want decoupled. This VDD should not go to the output. This VDD should not go to the output. So I just decoupled it. Is that okay? This VDD should not go to V0, so I have stopped it. Is that okay? At this point, please remember there is a DC plus AC. Is that correct? We are only calculating AC is fine, but at this point both AC plus DC are available to you. That means on this whatever DC voltage, AC is running over it, and that DC I want to make it 0. So I pass through a capacitor and only AC is bypassed. Okay, is that clear? So that is exactly what we are doing. Okay, what is the purpose of this CG compared to this RG? Because whenever DC part is concerned, I want this to operate, but when I want AC, I do not want that to be considered in my calculations. Because if there is no RG, this current source cannot provide that bias to it. So I must show you there is an RG sitting there. Okay. If you wish, you can see the way circuit could be also looked into. ऐसा भी देख सकते हो. Sorry, अभी नहीं, ऐसा दिखाना पड़ेगा. Okay, this is source side, this is drain side, and this is gate side. Is that correct? This is source, this is gate, this is drain. Okay. यानी 90 degree मैंने ऐसा घुमा दिया circuit because I want to draw equivalent of that. So जैसा, please remember how do I draw equivalent circuits? I actually see the main circuit and equivalently put the components down. Is that correct? That is easier to do. If I do something and then I start drawing 90 degree, then वो ऊपर ये किधर ऐसा. That's why I always try to show you that the way I draw main circuit, the equivalent should follow. Okay, that is easier to draw. No reason why you cannot show circuit like this. You can always show like this. That is absolutely correct. Okay, but for my simplicity, I always show you कि ठीक है जैसा बनाना है वैसे ही. Input you want to give from here at this side, so input. Output you want to collect here. This should be common gate. Is that okay? Drawing the circuit is identical. Only thing is 90 degree shift कर दिया मैंने उसको. Okay. This is your signal source resistance. Okay. This is of course DC, so nothing to be drawn. Here between source and gate is grounded. Please remember gate is grounded. RG is bypass for this, so gate is grounded. Source is this terminal. VGS exists between source and gate. Okay. What should be polarity of VGS? Gate plus, source minus. This has to be always correctly drawn. Okay. VGS. From source to drain, there is a current source, and how does it flow from drain to source? आपके सर्किट में भी ड्रेन टू सोर्स ही दिखा है ना, अब ये ऐसा कर दिया बस. So drain to source, so this is GM times VGS. Okay, This is your RD. यहाँ ऐसा दिखा के ग्राउंड करते थे नॉर्मली, इसमें थोड़ा ऐसा करके नीचे ग्राउंड कर दिया. And this is your external load which is also grounded. Is that okay? So the equivalent circuit, is that clear to you? How do I do? Why I draw this circuit like this? Because then I can draw this circuit almost identically down. Is that correct? So please remember that this is not relevant per se as far as circuit and a board is concerned. Okay, but for drawing this, if you draw this, you know much better how to draw equivalent. We are not interested in this, we are interested in this. So we want to know what is it, okay. Where, yeah, you are right. Between source and drain there is a R0. Right now our assumption is R0 is very high. Yeah, absolutely no problem. No, it only creates problem of solving equations. Now you remember, not only current path is this, but also part in the R0, okay, part in the R0. You are right. What did I tell you in the class first day? I will solve simpler problems and I will ask you higher difficult problems. ना? So मेरे लिए मैंने अपना simplification दिया. Okay, is that okay? So let's do that quickly analysis now. Keep that circuit in front of you. Vn, please remember Vn, if this is the IN current, this drop plus this drop. Is that okay? Vn, II, this drop, and why minus sign I put? Because this is minus plus VGS from here, on the top it is minus VGS. So this drop minus VGS is your Vn. Is that okay? Last people, is that okay? This voltage is equal to this plus this, okay, both sides go on ground, okay. Okay. From the input loop. However, this IN, actually I may be calling II or IN is same. Is there any other source you see from here? What is IN actually? Current in this circuit, if her problem is then little different, but let's say R0 is infinite, then this current and this current are identical but in opposite polarity. GM VGS is entering here, IN is entering here, they are same currents, there is no other current source here, okay. So we say II or IN, maybe if I made IN, call it IN everywhere, okay. But IN is minus GM VGS and therefore I substitute this IN here. IN is minus GM VGS. So Vn is IN RSC, I replace IN by GM VGS, GM RSC plus 1 into VGS. Is that okay? So how much is VGS? Minus, how much is VGS? Minus Vn upon 1 plus GM RSC. Is that correct? So how much will be VGS Vn related if RSC is 0? They will be equal. Okay, phase out, but they will be equal. By magnitude wise, they will be equal. So that question is always there. If RSC is made 0, just make RSC 0 now instead of initially doing. Right now you can say, so generalize this, put RSC 0. Okay. So V0 is, how much is V0 from the circuit? Can you tell me? Minus GM VGS will pass through this. Is that correct? Why minus? Current is going out from here. So the drop across this is minus GM VGS RO parallel RL. GM VGS RD, so not RO, RD parallel RL. VGS I have just calculated. VGS I have just calculated. Is it okay? Third bench, is it okay? So VGS is minus V in 1 plus GM RSC and V0 is minus GM VGS RD parallel RL. Okay. So what do I now do? Put this VGS here. Then I have V0 in terms of Vin. Is that correct? V0 in terms of Vin. Is it okay? What is the phase difference in the case of MOS transistors between drain current and source current? same. So V0 Vin का गेन कैसा आना चाहिए, पॉजिटिव आना चाहिए ना, क्योंकि ये एक ही डायरेक्शन में नीचे जा रहे हैं सब. सोर्स पे इनपुट है, ड्रेन पे आउटपुट है, सेम सेंस में जाना चाहिए. आता है क्या देख लेते हैं. इज दैट क्लियर? Since the drain to source current is same direction, if I input at source and collect the same side on the there, they should be of the same signs. Let's see whether it comes. It see because it is minus, ये minus इसमें रखेंगे, so that may become plus. So V0 is minus GMRD parallel RL into minus Vin upon 1 plus GMRC. So the voltage gain is plus GMRD parallel RL upon 1 plus GMRC. Please remember once again V0 and Vin are in phase. So in common gate, what is that we have achieved? In phase outputs. Okay. How much is the gain really will be? Assuming RS is 0, it is still GM times RD parallel RL as normal amplifiers. Is that correct? But what is important here, where this will be used very often, is this. Find the current gain for this. I0 by IN. ये exercise है. All amplifiers, though I did not calculate, maybe next some of them I will say, we must calculate all 4 terms. Which are 4 terms I said? Can you tell me? Voltage gain, current gain, input resistance and output resistance. And if there are capacitance, what should be new name should be input impedance and output impedance. Okay. So we must calculate all 4 quantities. In some cases, we may do 2 more quantities also. Which can be 2 more in gains? Input current, output voltage. Input voltage, output current. I0 by Vin, V0 by IN. So 4 part, transconductance, transresistance, voltage gain, current gain. There are 4 possible gains in an amplifier. Is that clear? Now at times we want to use them as a current amplifiers, at times I want to use them as a voltage amplifiers, at times I want to use amplifier as a transconductance amplifier, and at times I want to use a transresistance amplifiers. Each has a different applications. Then we will say one of them which dominates when. So I want this kind, so common gate is better, or this is better, or that is better, which I should use for this. There will be only 3 of this kind, with of course source degeneration, 4th one. But any one of them should be chosen corresponding to the kind of gain maximization you are looking for. Okay, is that clear? In analog, what are we looking? 4 possible gains, and see whether it matches one of your 4 combinations available to you. Okay, whichever gives you better results, use that. For us, what is it? Yeah, current equivalent circuit, we can always calculate anything to anything, ratio of anything, you tell us. Okay. So we must evaluate all 4 of them and keep ready. So such tables are available in books. Okay. That is what all designers do. अरे क्या लिखा है? सोचते भी नहीं क्या लिखा? क्या लिखा है? ये ठीक ही है. That is how 80% designers fail in the life actually, because they never think that your condition is whether exactly same as what they wrote. Okay. I0 is current through the load. Okay, but that since the other resistance is parallel, the net current at the output. Please remember, no, she has a, I think we must honor her words. We should not take, this is something like this. Is that correct? This is the output. They may have a divisions. Is that correct? The current output is here. Is that correct? So you must take output at the output. Okay. Net current. So it may divide into RE, it may divide into R0, it may divide many parts, but the net current is I0. Is that okay? No. They are in parallel. Why should it only be there? There will be 3 parts coming. GM, VGS will actually divide into 3 parts. So the I0 is actually at the output terminal and not through the load resistance. The output terminal. You are very correct. But let's look at it. See the current in this, whatever current coming from here will divide into this. So this current is what is outputted from the transistor. This ratio I am looking for. Gains are always connected from the drain side. Voltages, everything we measure here. So at the drain, current coming out is how much? Is that correct? So this is my I0 and this may divide. So the net current, if I put a one node here, net current is essentially entering two paths. Okay. What you are saying, why not only this? Okay, you calculate even for this, doesn't matter. This will be actual load current which you are looking for. This is also possible. But when I say something, I say I0 here. Okay? Yes. For the oh yeah, it's called short circuit current, ISC. Okay, that is another way of solving a circuit. Maybe one day I will spend on how to use only open circuit and a short circuits values. Okay. That is a much easier method of solving larger circuits. I am avoiding all of them simply because in my opinion, if you do this kind of analysis, it never gets into an error. Okay. That is the method I suggest you, because in my opinion, Kirchhoff law solving is the easiest on such systems. Is that clear? I am not suggesting, there are three more methods I can show you. For example, people don't use GMs. People use GM R0 as the output voltage sources. There are different ways of doing things. I am showing you my simpler method to tell you that if you want to make zero error free solutions, use this equivalent circuit and solve, which will never get into an error. Is that okay? For this, the input resistance is VGS by Rn, but Rn is minus Gm VGS, so Rn is 1 upon Gm. Is that correct? Minus VGS is Vn, that's what we said. Gm VGS is In, VGS by In is the Rn, so Rn is 1 upon Gm. How much is the output resistance? Output resistance method is, what is the method I suggest? Short the input source. Since there is no current here, this is grounded, this is very small, no VGS, therefore no GM VGS. So RD is the only resistance there, the R out is RD. Okay, Vx by Ix is RD only. Okay. How much is the GM value in transistors? Other day we calculated, not in bipolar. In the case of MOS transistor, what is typical value of GMs? Order. QIC by KT जो GM है उसमें भी मिलीएम्प्स में आते कुछ कितना 38 मिलीवोल्ट मिलीएम्प्स पर वोल्ट आया था तो मास में क्या ज्यादा होगा कि कम होगा? कम होगा ना. So it is of the order of 10 to power minus 4 or 10 to power minus 5 amps per volts. Is that clear? So Rn 1 upon Gm is of the order of 100k. Rn is of the order of 10k to 100k. Is that clear? That value you should know typically of the order of 10k to 100k. Depends on the bias current you are using. Is that correct? It will decide on that. And RD of course is the RD value used for biasing as well as for the load. So whatever is RD is your output resistance. Is that okay? So what is the advantage of common gate you saw from here? The voltage gains, how much was the voltage gain we said? GM RD parallel RL. Is that correct? That was the voltage gain. So which is like a normal amplifier. But it is in phase. Its output resistance is low, its input resistance is high. Is that clear? What did we do by common gate? The gain is like a normal amplifier, its in resistance is relatively high and its output resistance is now controllable by me. How much RD I fix, that's my R0. Okay, that's exactly what it is, and it is in phase and therefore no problems of connectivity. Is that correct? Circuit can be connected directly from left to right. Okay, that's the biggest advantage common gate gives. Another thing which is not showing here and we are not started, which is called frequency response. Something else will happen for all three amplifiers. Some may have larger bandwidth, some may have smaller bandwidths. Okay, so when the bandwidth issue comes, again we will have to make a choice which one to use. Okay, So that is the way we must look at it. Okay. Before we quit this area, quickly I'll not solve all of it. There are different kinds of load, I say, in the case of MOS amplifiers. One of the MOS amplifier will have, okay, by the way, this terminology you should use. Where input is connected, that transistor is called driver, okay, and the resistance is replaced by a transistor, that is called load. Okay, it's like a load. Okay, this is called driver, that's called load. This is actually equivalent of this, nothing great and nothing very big. Okay, this is our load, this is input, this is my driver, this is my output. Okay, this is the symbol, this is what we'll do. So how to make saturated load? I say if gate is connected to drain, VGS minus VT will be always less than VDS by design, therefore always in saturation. So normally this source is equal, when I say I short this to get the resistance here, this is like an infinite resistance here, which means if this RS in a common source with source not bypassed is equivalently, so you do this analysis for this Vx by Rx, Rx will be equal to 1 upon Gm parallel R0. Which one will be dominating in this or this? बोलो है, अभी बोला ना, Gm 1 upon Gm कितना होगा? 10k to 100k. How much will be R0? Mega ohms. So typically this will be always equal to 1 upon Gm. Is that correct? So इसको इक्वलेंट रिप्लेस करने के लिए क्या रिप्लेस कर सकते हैं? 1 upon Gm. Is that correct? A saturated transistor load is equivalent of 1 upon Gm. Of course, if R0 is not very high, then parallel whatever it comes. Okay, but if it is R0 is very high, then you can say it is almost 1 upon Gm. हाँ थोड़ा मैंने यहाँ थोड़ा सा हिंट दिया है ना. This driver acts like a series resistance for this amplifier or this transistor, and since there is no current will flow because Vin is going to be 0, this is equivalent of infinite resistance. ठीक है, तो थोड़ा सोच लिया करो. Why I don't say everything? Because I thought you should think. मैंने आपको हिंट सब दे दिया कि क्यों कर रहा हूँ, थोड़ा सोचोगे. हाँ, this is called equivalence resistance is the source of a load which is infinite. I just told her, think of it, why this is equivalent of an infinity. This RS is tending to infinite. थोड़ा सोचो क्यों ऐसा सोच के इक्विवेलेंट बनाया मैंने. मेरा थोड़ा सा टेक्निक है कि मैं ऐसा देख के कुछ नया बता दूंगा, ऐसा आपको बुक में नहीं मिलेगा. ऐसा what I am showing you is not given in a book. This is what you visualize. How do I visualize? Oh, that means this is equivalent of that. This is what I give you hints, okay, how to visualize. Let's go quickly on the gains of this. Here is very interesting equivalence of this. Gm VGS is the source. There is no source resistance, so directly VGS is Vn. Gm VGS. What is this ROD? Driver output resistance. Okay. What is these two? Why I am drawing from the same terminal? This is the drain. Please look at it. This terminal is the drain. This is ground for AC. So whatever this load resistance is appearing here across to the ground. Is that clear? Is that point clear? ऊपर ground है तो उसको नीचे fold कर दो. Ground नीचे ले आओ. ठीक है? So that's exactly what this circuit shows. This is ground. Lower terminal is ground. So Gm VGS ROD 1 upon GML ROL. I repeat, this ROL can be larger or not larger compared to 1 upon GML. Check it before actually leaving or not leaving terms. Okay. Alternatively, if you say ROD is much larger than 1 upon GMD, ROL is much larger than 1 upon GM, then one can show, and this also I will not show for you, that V0 by Vn is GMD, or you do not have to say, you remove these two RO and ROD, then GMVGS passes through 1 upon GML. Is that clear? If you open ROD and ROL, this current passes through only GML, is that 1 upon GML. So the output resistance, output voltage is 1 upon GMD upon GML. Okay. What is GMD? The transconductance of the driver, 2 beta n dash W by L driver into the bias current IDSQ divided by GML, 2 beta n dash W by IDSQ. What is this IDSQ? The operating which we are not shown, DC bias part we are not shown, that is the bias current. Okay. So how much is the gain essentially in the case of NMOS these amplifiers? Under root of size of driver, W by L of driver divided by W by L of loads. So gain बढ़ाने के लिए क्या करना चाहिए? Size of driver should be higher compared to the load. Is that okay? So driver W by L इतना बड़ा बनाओ और लोड इतना सा लगाओ तो गेन बढ़ जाएगा. That is how we do gain adjustment in silicon chips. An NMOS amplifier on a silicon, all that I will design an amplifier of this kind and change the sizes, okay, to get my gains. Is that correct? Do you also see interestingly here there is no device parameter, basic technology device parameter except W by L, which is size, which is controlling it. Sizes of course can vary. This also is a problem. This W by L and these W by L's may not be accurately put on the silicon, then the actual gain may not be exact, but this under root may help you. Please remember, under root reduces something but it also reduces the error. Okay. That's the advantage you must look into. Something which is bad for you, उसमें अच्छा क्या है? Error कम होता है. Is that okay? So this is called, what are the other loads I can use? This was NMOS enhancement mode. What the other load I can use? NMOS linear mode, VGG लगाओ. उसका I have already calculated R for linear circuits, so put that R there, 1 upon beta VGS minus VT. That value we know, so we know what is our load for that. What is the third possibility? ये एक और है, depletion load. उसका भी R निकाला जा सकता है. We can replace depletion loads, and finally we can use P channels with N channel together, and that is what CMOS inverters are all about. We normally use CMOS amplifiers for full range, we call it inverter. If you only use the transition, we say amplifier. Okay. There is no difference between the two. Okay, the other amplifiers, please look into the book which has my name also. Okay, before we quit for the day, there is one interesting thing I said you earlier. For a normal amplifier, omega T, which is the figure of merit, what is the omega T means? Unity gain into bandwidth, or it's called gain bandwidth. Okay, omega T is essentially gain bandwidth. How much is that I said? Roughly GM by C, Cn or whatever equivalent. Okay. This is what we said. Fair enough. So what is the figure of merit? I say omega T. Okay. So if I increase gain, I reduce bandwidth. If I increase bandwidth, if I increase gain, reduce bandwidth. If I increase bandwidth, I reduce gain, because this is fixed. Is that clear? But that is limitation you said, na? So essentially I said that is the maximum frequency up to which one gain at least should be seen. You can't go beyond. Now this is creating a problem. I want larger gain, okay, but I don't want bandwidth to be lost. So something, let's say, we are not talked about right now, gain versus frequency, okay. But what we are essentially, we will see later, but assuming for a op-amp, this is omega T, this is 0 dB, this is called Bode's plot, which we are going to do soon, okay. frequency response of a gain function. So whenever gain becomes unity, we say it's the ft or omega t. What really I want is or if not this, is that correct? What I am looking for, I may have this frequency where fall occurs may be slightly reduced, but the gain is higher, but it should roll down exactly at the same point. Is that correct? So I want, what is it called? Gain boosting. What we did here is gain boosting, but what we did not lose? ft. Is that correct? नॉर्मल एम्पलीफायर में तो ऐसा हो ही नहीं सकता ना, इसके किधर भी जाओ तो गेन तो कम या ज्यादा हो ही जाएगा. सो आई वांट टू सी कैन आई डू दिस मिस्चीफ नाउ or can I break this what is called as technology constraint. What is constraint? This is constraint. I want to break this. Here is the circuit which does that. Okay. Please remember what the amplifier which is now going to be taught is essentially what is going to do it. It may boost the gain but will not affect FT. Is that correct? If I do that, then what I did it, I have broken this technology constraint. Okay. बट सम कॉस्ट क्या दे रहा हूँ, इसका जो रोल ओवर पॉइंट है वो थोड़ा कम हो जाएगा, पहला पोल जिसको बोलेंगे वो थोड़ा लेफ्ट में आ जाएगा. बट इफ कैन आई कैन स्टिल डू दैट, दैट मे बी स्टिल एक्सेप्टेबल टू मी, देन आई हैव गेन बूस्टिंग पॉसिबल. ओके, दिस इज एसेंशियली डन बाय एन एम्पलीफायर कॉल्ड cascade. Okay, what is cascade? I repeat, if someone says cascade, which we have to do but we are not done, essentially A1, A2, A3, इसका इनपुट, इसका आउटपुट, नेक्स्ट का इनपुट, नेक्स्ट का आउटपुट, नेक्स्ट का इनपुट, दिस इज कॉल्ड कास्केड. रेलवे ट्रेन एक के पीछे कास्केडिंग. ओके, व्हाट इज द गेन इन सच केसेस? A will be A1, A2, A3. Is that correct? In cascade, but then as you boost the gain, what will according to this will happen? The bandwidth कम हो जाएगा. ठीक है. Now I want to see gain boost but not losing bandwidths. Okay. So let's see whether difference between cascade. Remember why I showed you immediately this. What is that I am achieving in cascade? Enhanced gain. Is that correct? Here also I am enhancing the gain. Is that correct? So enhancement of gain is my aim, but in the first case I don't lose my bandwidths or I don't lose my WT, but in the next I will finally, because it will start rolling down earlier and earlier. So finally it may actually become somewhere like this. I don't want that to happen. Sorry. So I don't want to use that kind of things. Okay. So cascade नहीं करना चाहता मैं, cascade कर. Okay. थोड़ा सा इंट्रोड्यूस करते, नेक्स्ट टाइम कैलकुलेट करेंगे. इस बार थोड़ा एक फिगर बना देते हैं जिससे आपको आइडिया लग जाए कि मैं इतना गप क्यों मार रहा हूँ. और why I showed you this common gate will be now visible to you. Here is the device. Okay, another source, another way of biasing MOS transistor, if you recollect, I showed you by mirrors or what we saw as current sources. So many times bias I is that okay? This is also biased by current source I. From this current, from where it can come? From the mirror. Okay, from the mirror. Okay. So let's see, I take a easier case first, maybe I can replace transistor later, P channel or N channel. This is the current source IDS which is biasing the device, and now I have two transistors in series. First is driver and second I actually apply what we call V reference. V reference is DC volt. Is that clear? V reference is a DC bias for what? Create VGS for here, okay. Which is for AC, what is the terminal going? This terminal? Ground. Common gate में क्या बोला था आपको? Gate is common to both. Gate is common to this, gate is common to this. Is that clear? So ये तो हो गया common source. Lower transistor is acting like a common source. Call it M1, M2 for example, M1 and M2. So M1 is common source system, but M2 is common gate. Is that okay? Actually digital circuit में इसको क्या बोलते हैं ऐसे actually लिया तो पढ़ा है क्या आपको भी? What is this called? This is called transmission gate or a pass gate. Whole logic depends on this pass gate. So whatever is V in will be transferred to V out when the phi goes 1. If phi is 0, V out is the last V out. Is that correct? There is a transistor doesn't conduct. Okay. This is called pass gate in digital. This is what we use very often in digital. Okay. Here, this is like, now think of it. If this so-called M2 would not have been there, this is like a normal amplifier, a bias equivalent resistor, RO of this series to this driver. This is RO of this series to this. Okay. So this is a normal NMOS amplifier with a load of R0. But now I put M2 in between. So what is the way gain can be improved in this? Because there is no external load in the case of such circuits. The gain, I said you how much? Gain of such amplifiers are GM times R0. Please remember R0 is the resistance of source, current source. Okay. So GM times R0 is this. इसको बढ़ाना है मुझे, पर यदि मैं इसको बढ़ाता है तो इसको I can increase by increasing sizes, but if I increase sizes what will happen? Capacitance will go higher, so GM by C will not improve for me. Okay, so what I say, okay, I damn care about this, but can I boost R0? Please remember what I am trying. I will boost R0 so that my this increases, GM R0 enhances if this is R0 dash. Okay, but GM I kept roughly same as what earlier. Without this, with this together GM, if what is the GM for this full of this? Delta IDS by delta VGS is still GM. Now together का करना है. Okay. So if I maintain GM new equal to GM old, what I am going to get? Bandwidth will be, WT will be affected or not affected? No, no area change. GM is same, C is same. So FT I fixed it otherwise. But what I boosted is R0. So what I boost? I will boost gain. So now I have broken it. I have improved the gain, but I have not lost FT. So this circuit essentially enhances the output resistance. Is that correct? This circuit essentially enhances output resistance, huge number. Okay. Gain times R0. This will be gain times R0, gain of this into R0 will be appearing as the new R0. Okay. So gain will be boosted, but FT will not be changing. Is that clear the game? If I change GM, then I have a problem because then I have changed both. Okay. But if I fix my GM, then I don't change FT or don't change bandwidth for that matter. But what I'll change? Gains. R0 बढ़ा दिया. Cascades enhances the output resistance without losing GMs. So this M2 allows, what is called cascade, allows you to boost the R0 of the circuit. Is that correct? Next time we'll calculate this. Okay.